Today we're going to shift gears a little bit and perform a lab where we're going to try to verify the law of conservation of momentum, the law that we've been talking about for the last 2 days in class. So you can imagine if we're trying to verify the law of conservation of momentum, our problem, which is always phrased in the form of a question, will be, is the law of conservation of momentum valid? Now, we're only going to test the collision of two particular objects, so we're not necessarily making a generalization to every collision with the activity that we perform, but for two particular objects, two dynamics carts that we're going to collide, is the law of conservation of momentum valid? That's our problem. You can write it down exactly in the words that I've written it down here. That's absolutely fine. Now, you guys know from Physics 20 and from Science 10 for that matter, the next thing that we write down in a full lab write-up would be our variables. We're testing to see if the final momentum equals the initial momentum. What we're effectively going to do in this activity is send one dynamics cart down towards another. We're going to cause it to collide, stick together, and then see what the final momentum is and essentially compare it to the initial momentum. What do you think we're going to change in this activity? What do you think that we're going to manipulate in this activity when we're sending one cart down to collide with another cart, stick together, and then see how they go off? What velocity, initial or final? Are we changing the final velocity, John? We're changing the initial velocity, but be careful with that before you write that down. We're changing the initial velocity, but the whole point of changing the initial velocity is to manipulate the initial, not velocity, but momentum, right? We're changing, ultimately, the initial momentum. So my initial, or my manipulated variable would be the initial momentum. Now, what do you think is going to respond to that? What do you think is going to change because we changed the initial momentum of the car? John? The final momentum, right? The final momentum responds to the initial momentum. Now, the control variables are everything else that remains the same. So I'm not going to go through a list of those. You could come up with 3, 4, 5 of those, whatever. There are a few, 1 or 2 control variables that are really important. You've got to keep these the same, otherwise all bets are off, right? We can't do anything with this activity unless you keep this and this the same. I'm going to let you think about that as you're performing the lab. Now, just a little suggestion for you. As you perform in the lab and as you're thinking, oh, I can't change this, write that down. Make a little note of that, right? Because when you go to write this up next week, when I'm not even around because you have next week off, you're going to be struggling sometimes to think of exactly what you did in this activity. If you write down little notes like, oh, I kept this constant, I kept this the same, oh, this could be a good source of error, then it's going to be a lot easier for you to write this up, in 5 days or a week's time. Your apparatus, your materials, is going to look essentially like what you see up on the board here now. There is going to be a triple beam balance scale. Notice that I haven't even put a materials actually. I've just put it under procedure here, but we're going to kind of combine them for purposes of telling you what we're going to do in the lab here today. You're going to separate them, right? You're going to have materials, and then you're going to have procedure. Tell you what I'd do. For materials, what I would do is exactly what I've done right here. I would snap a picture of it with your phone. I would insert that picture into your document. Now, it's not good enough to just do that. You have to list what things are, but that prevents you from forgetting anything, right? If you take a picture of it, you insert it into your document, and you start labeling that picture, all of a sudden, hey, oh, I was going to forget this triple beam balance scale. Well, you can't forget it anymore because you see it right in your picture. This is our triple beam balance scale. This is going to be what we call an air link. And I'll explain what that's for in just a second here. This is what we call a motion sensor. The motion sensor is connected to the air link. The air link is connected via Bluetooth to your iPhone. So over here somewhere, you're going to have your iPhone. Your iPhone is what you're actually going to view your data on. The motion sensor measures the position of the dynamics cart. The motion sensor transfers the data via a cord to the AirLink, and then the AirLink is going to transfer the data via Bluetooth to your iPhone, and you're going to view it on your iPhone. Then you're going to transfer it to a computer later on, but in the lab itself, you're going to view it on your iPhone. Now, what data are you going to collect? Well, we have to have two carts colliding, right? So we're going to have cart number 1, and we're going to have cart number 2. Cart number 2 is going to be initially at rest in all of your trials. Cart number 1 is going to be propelled by your hand towards cart number 2 at a different speed for each trial. So we're going to send it down away from the motion sensor toward cart number 2 at a certain speed. We're going to record that data. Then we're going to do it again, repeat that trial, except we're going to send cart number 1 down toward cart number 2 at a different speed. Now, how are we going to make them stick together? Well, when you look around the school, there's lots of stuff on teachers' walls sometimes. Not so much on my wall, but when you look around some classrooms, there's lots of stuff on teachers' walls. We're told we're not supposed to staple into walls because it makes little holes in the walls. What we're supposed to use is this little blue sticky tack stuff. Okay, that's what you're going to use to make these two carts stick together, is blue sticky tack on both carts. Put it on both carts so that when blue sticky tack hits blue sticky tack, they're going to stick together and head off as one object. Now, the final material that you're going to use here is going to be a track, a dynamics track. Now, your track may look exactly like the one that you see up on the board right now, or it may be one of these wooden dynamics tracks that Mr. Kader and I built ourselves. Depends upon which kind of cart you're using here, okay? Doesn't really matter. Okay, they're both going to work just fine. Doesn't matter which one you're using. Just depends upon which kind of cart you're using. If you're using this kind of cart, let's use the metal track. If you're using this kind of cart, let's use the wooden tracks. All right? One more little thing here, guys. This is a magnified version of this motion sensor over here. Make sure the switch, it probably is already in the right place, but if it's not, make sure the switch is right here. Okay, that allows us to measure the position of something small and relatively nearby. If the switch is in the wrong place, let's say it's over here, then that's going to allow us to measure the position of maybe something bigger and further off, somebody walking across the room. That's not what we're trying to do here today. So make sure it's in the right place. It should already be in the right place, but don't trust the last person who's done a lab to have made sure that it's in the right place. You make sure yourself that that switch is in the right place. So there's the apparatus. The procedure I've pretty much described already. Essentially what you're going to do is set up the apparatus as we demonstrated it to you. We're going to make sure that cart number 2 is on the track at rest. We're going to make sure that cart number 1 is close to the motion sensor. We're going to send cart number 1 toward cart number 2. They're going to collide. They're going to stick together. They're going to head off as one object. We're going to measure the position and time of those carts. Then we're going to repeat that again and again and again, changing each time the initial velocity of cart number 1 or the initial momentum of cart number 1. Does that make sense? Now, in the procedure that I just described, we haven't mentioned this. We haven't mentioned this triple beam balance scale. What do you think that's for? What's that for, Rucker? Yeah, we got to find the mass of the carts. Okay? Got to find the mass of the carts. And you're going to have to record the mass of those carts. Again, you have a picture of this, you're a lot less likely to forget something like that too. Hey, I got to measure the mass of the carts. Oh yeah, I got a triple beam balance scale. That makes sense. I got to measure the mass of the carts. Question? We'll talk about that in a second. Yeah. So far, so good? All right. When you collect data, you should see a graph that looks something like this. It may not be exactly like this, but something like this for each trial. And I want you to have ideally 10 trials, but if we don't quite get that far, we get 6 or 7 trials, I can live with that. But for each trial, you should get a graph that looks like this. More or less, at least, that looks like this. Now, sometimes you might even see something, some points that kind of go beyond like this. The part of the graph that I'm concerned about is this part and this part. This part corresponds to before the cart actually started moving. In other words, the velocity was 0. We don't care about that. Okay, we don't care about the data that we collected before we actually pushed the cart. This would correspond to after the cart was either slowing down or maybe it even stopped because of friction. We don't care about that data either. That's irrelevant as well. We want to get rid of that. This would correspond to the initial velocity of cart number 1, and this would correspond to the final velocity of cart 1 and 2 combined. Notice that the final velocity has a smaller slope than the initial velocity, which makes sense, right? If cart number 1 is moving at a certain speed, it hits cart number 2, sticks together, the final velocity of the combined mass will be smaller than the initial velocity of cart number 1. You're going to need to, for each trial, and I'll show you how to do this after you've actually collected your data, not right now, but you're going to need to, for each trial, obtain the initial velocity. Get what the initial velocity is for each trial. And you're going to have to do the same thing for the final velocity of each trial. And then you're going to create a table. Your table will include the 2 masses that we've measured with the triple beam balance scale. And it will include the initial velocity of cart number 1, which we get from this, and the final velocity of both carts combined, which we're going to get from this. That gives us trial 1. Then we have to do that all over again for trial 2, and for trial 3, and so on. Ideally, 10 trials, but depending upon time, we may find ourselves accepting 6 or 7 trials. What do you think we're going to do next? What do we always do when we have a data table? Analysis, yeah, but a data table almost always leads to what kind of analysis? A graph. The graph we're going to plot is VF versus VI. There's a new graph you've never plotted before. And I'm going to show you how to do the analysis on this VF versus VI graph. You've never done this before. Never done this before. Although it's not crazy hard. The graph that you will get on this VF versus VI should be pretty much a straight line. Now, all of you guys know from grade 9, maybe even grade 8, what the equation for a straight line graph is. Every straight line graph. I don't care whether it's VF versus VI, or D versus T, or P versus Q, or Y versus X. I don't care. The equation for any straight line is what? Y equals mx plus b. Good. So let's write that down. From our graph, we get an equation, y equals mx plus b. Now what we want to do here is replace y with whatever appears on our y-axis. That's VF. M, I don't want to use the term M. That's slope, right? I don't want to use the variable M here because I might get that mixed up with mass. So I'm going to change that slope into literally the word slope, just so I don't get it mixed up with mass. X is going to be whatever appears on my x-axis, which is V1 initial. Plus B. What's B? Yep. The starting point on the y-axis, or in other words, the y-intercept. there will not be a y-intercept for this, at least not of an appreciable value. So you're not going to have to worry about the y-intercept in this. You're going to be able to scratch that out. So y equals mx becomes vf is equal to the slope times v1i. Now what you're going to do is come up with an equation from your data sheet or from some other concept. The relevant equation here is pi is equal to pf, conservation of momentum. We're going to say m1 v1i plus 0, because the second object wasn't moving before the collision, equals mvf, m being the total mass there. Let's go at mt actually, just so you remember that that's the total mass, m1 plus m2. Now what I want to do is rearrange that equation for the same variable as I got for my graph. So it's going to be vf is equal to m1 over mt times v1i. Now we're going to cross off things that appear in both. vf appears in both. vi appears in both. What are we left with? The slope of this graph is equal to m over mass total. Sorry, this would be mass 1 over mass total. We can get the slope either by going rise over run or using the spreadsheet to spit it out for us. We can get the value of the slope. We've got the value of mass 1. We've got mt, the total mass. Here's what you're ultimately going to do, and this is the crux of proving whether conservation of momentum was valid or not. You're going to take this number, and you're going to compare it to this number. If those two numbers are the same, if the slope of this graph does equal m1 over the total mass, then the law of conservation of momentum must be valid. We assumed it to be valid here, right? In order to get this relationship, we assumed the law of conservation of momentum is valid. If our assumption is correct, then those two numbers, slope and m1 over mt, should be equal. If they are equal, then our assumption must have been correct, and we've just proven the law of conservation of momentum. Now we need conclusion. Was the law of conservation of momentum verified for the collision of two dynamics carts, and how do you know? Was it verified? Well, if the slope was equal to m1 over mt, yes, it was verified. If the slope wasn't equal to m1 over mt, then no, it wasn't verified. What if they're not exactly, but they're really, really close? Well, let's do this. Let's calculate a percent difference. You guys ever done that in chemistry class? You guys seen this equation? Actual minus theoretical over theoretical times 100. You guys ever seen that? Yes? The actual value will be what? Slope or m1 over mt? Theoretically, the slope should equal m1 over mt. This is going to be the theoretical value. This is going to be the slope. If that percent difference is within 10%, okay, if it's less than 10%, then we're going to say yes, momentum was conserved. If it's greater than 10%, then we're going to say no, momentum was not conserved. Of course, the last thing you need in here is sources of error. Give me 2 or 3 good sources of error, things that either went wrong or could could have been done better? Give me a couple sources of error and then ways to improve those sources of error. Jack, question? No, that's a great question, actually. That's a great question. That percent difference calculation should go where? In your analysis or your conclusion? It should go in your analysis, right? You're basing your conclusion on that, but that is absolutely still part of your analysis. So there's a lot to this. There's a lot to this, but the good news is you've got a lot of time. It's before break here. It's not going to be due before the break. It's going to be due a couple of days after the break, in fact. So you've got virtually 2 weeks to do this. Let's go back here real quick. That's one trial, right? You're going to get up to 10 of these. 10 initial velocities, 10 final velocities that you're going to plug into this table. Then you're going to plot another graph, which is based on this table, VF versus VI. And then you're going to do the analysis for that graph to determine the slope, which your spreadsheet will spit out for you, M1 over MT, which you're just going to do on your calculator, and then you're going to compare those two values using the percent difference equation. Do I want to see all of these graphs? That's a good question. When we go through the procedure for plotting graphs and so on, I'll give you more detail about that, and I want to do that after you've actually collected data because I don't want to overwhelm you any more than I already have yet. But the bottom line is this. I don't need to see all of these graphs in your write-up. You should keep these graphs in case something goes wrong and in case something isn't working out so that you can go back and look at them and see where you made a mistake so you can fix it. But I don't need to see that. Okay, that's going to make for a 10 or 20 page lab write-up, and I don't need to see that. Okay, what I need to see is these, okay, the numbers that you get from that.